All right, since we're on alternating series, it's a good time to introduce the alternating series estimation theorem, which will come back later in this unit when we really dive into approximation and errors in our approximation. But while we're on the concept of the alternating series, we're going to talk about the fact that if we have a series that is alternating and converges absolutely, that means it converges even without the alternator, then the sum of the series can be approximated using the values of the terms with an error that is the absolute value of the first unused term. So this example we're given, I don't know how to find the sum of this series. The only series that I know how to find the sum of are either geometric or telescoping. This is neither. So what I can do is that I can approximate the sum by adding a finite number of terms in the series. Now here I'm adding from where n equals 1 up through when n equals 9. So I'm adding up 9 terms here. And when I do this in my calculator, I get 0.828. So I'm approximating that the sum of this series is 0.828. The first term that I haven't used is going to be the n equals 10 term, which is 1 over 100. In fact, it's a negative 1 over 100 because my alternator goes positive, negative, negative. And the last term I had was addition, so the next term would be subtraction. So this is the first term I haven't used. Remember that the error in the estimation, or the maximum error in the estimation, is the absolute value of the first unused term, which is 1 over 100, or 0.01. So now what we're going to do is use our calculator to plug in this series and add the first 200 terms. And don't worry about this F3 calc, that's from a TI-89. I'm going to show you how to do this on a TI-84. I want you to go to alpha F2, and choice 2 here is the sigma for sum. And then isn't this nice? They have sigma notation set up for us. I'm going to go ahead and use X because it's easy, and that's what they've set up for me here. So I'm going to start with X equals 1 because that's our lower index. And I'm going to go up to the 200th term because that's what they asked me to do. So add up 200 terms. And then, of course, I have the actual equation that I need to type in next. So I'm going to open parentheses and put in a negative 1 raised to the x plus 1. And then multiply that by, in parentheses, 1 divided by x squared. Close parentheses. And I believe I have done everything correctly, and now we let it think. And it did not need to think long. It comes back to the approximate sum of 0.822. So 0.822. Oops, I just realized they're asking me to put that down here, 0.822. So this is really kind of cool because when we added just 9 terms, we said that the approximation was 0.828 and it differed by as much as 0.01, which basically gave us the information that the actual sum is going to be somewhere between 0.818 and 0.838 if I added and subtracted this error bound. When I added 200 terms, do you see how I got a sum that was exactly within that interval, which is as expected?